and do the screen share. Hectic morning. Okay. So here we go. Test is tomorrow. Tomorrow for in-class kids. There will not be a Zoom tomorrow. Okay. Take tomorrow off. Just use that time to study. Yeah, tomorrow afternoon, because they're just taking a test. Hold on, let me think. You'll be taking the test Friday, but yeah. So we'll take tomorrow off. You'll have the opportunity to take the test starting Friday at 1 p.m. But why would I say 1 p.m.? Why wouldn't I say 2? Because Friday we would have a normal Zoom. So I guess starting at 2 p.m., I will, around 2 p.m. tomorrow, Friday, I will send you a PDF. I'll email it to you, a PDF of the test. I'll also put some copies, paper copies, in the front porch. So if you don't have printer access, you can just stop by. You give yourself an hour to take that, just an hour. You got to be honest, because that's you got to be fair to your classmates that are suffering in class. Give yourself an hour, and then you bring it back. So if you want to come get it, you have until Saturday at 6 p.m. Saturday, 6 p.m. to get it done and get it back to me on the front porch. Okay, after that, it'd be considered late, which is pretty severe penalty on tests if they're late. Okay, so you can pick it up tomorrow, starting either from my front porch, or I'll send you the PDF. I'll have both, and it'll be available tomorrow, starting around 2 p.m. I'll start the process of sending it to you at 2 p.m. Okay. Yeah. So, but tomorrow, that's Friday. You just start at 2 p.m. Tomorrow, there won't be a one of these. All right. So it's class 15, Pkt4. Oh, before we did that, I did go over this again, because this is that Ask Me Tutoring, and it's starting to get a lot of people starting to sign up for it now. Juniors, and I had a couple sophomores say, "Can we do it?" Yes, you can do it. Seniors can do it too if they want, but we concentrate on juniors usually now, and then the junior will do it again in the fall. This is the last chance we'll do it. So if you want to, I'll put this in the screenshots, and you can click on that QR code and just put your camera on it. That'll take you to the website, or just go to askmetutoring.org. And that will assign, you can sign up there if you want. I mean, we're a private company, so we're nonprofit, but we still have to pay, our people. So it's anyway, so that's coming up next week, if you're interested. We did went around and did dog stamps for 3 and for 5, 1 for 3 and 2 for 5. For you all, this sheet is due for virtual. The whole thing is due tomorrow. I got to put this assignment in. This is a virtual assignment only, and this is due Wednesday, tomorrow night at 11:59. No, tonight. Okay, I'll cut you slack. We'll say Thursday. Tomorrow night, 11:59 p.m. Okay. And I don't know how many points it's worth. It's got to work out so it's the same, dog points per week. Anyway, tomorrow night, this is your weekly assignment. Due, finished. A lot of the keys are posted now on the Facebook and in our wrap-up videos. So the test the outline is done for tomorrow. We're not going to do that first one. because it got too convoluted. So there's 19 questions to choose from. I won't bring any other kind of questions in. I have chosen 9 of the 19. So there's 9 of these, and it's kind of now you got to play the game, right? Guess which ones which ones they are. Also, just make sure this is in your notes. You're going to turn these in your packet in a couple of weeks. This is where we're going towards. We did this in here on this Zoom. This is a free body diagram. This is where we're working our way towards. We have to learn a lot more about drag and lift and all that kind of stuff and friction. And so every one of these has their own, gravity. We just started talking about gravity. But eventually by April, I want to be doing these routinely. And then you do all the component method, and sometimes you do head to tail. And then this will lead us to work, which leads us to energy, which leads us to work kinetic energy theorem, which leads us eventually to power. And then we go from there, we go to machines and all that. And so theoretically, we would end the year in May if we get that far. If we don't, then I'll do through Ask Me Tutoring, I'll do a course in June, which will take us as far as and further actually than you need to go. And you'd walk into AP physics next year or into college physics, a lean, mean, fighting machine. Okay, so today we're going to do what, 3 or 4 things? One of the things we're going to do, though, is speaking of free body diagrams, the only thing we have left to do on 4.7, and remember 4.7 is what's due from you tomorrow night. All we have left to do is we're going to do number 2 together. So, okay. So we're going to do 2 together. Now, I want to do 2. I want to add these up 2 different ways. We'll start off showing these as a free body diagram. Okay. So in class we did this together. Let's make this our object, the dot for our object. I need I guess I can use the protractor that comes with the program. Okay. So, but no. Okay. This is about the right size. It's about the same as your paper. I'm gonna be off. The shape will be the same as yours. My scale will be off a little bit because this is not paper I'm looking at. This is a computer screen. And by the way, now 5 of my students have iPads, and they're doing all their physics with iPads, which is perfectly acceptable to me. And it helps in their homework. It doesn't help you on a test. But if you have iPads or if you have access to getting an iPad, like, you can get them now for $600, I guess, $500. It kind of makes vectors and stuff easier. You don't have to do it. You don't have to have it, but I'm just saying that now 5 students have them. All right, so here we go. So determine the resultant vector of these 3 forces using head to tail method. So first thing we're going to do is do as a free body diagram, and let's construct each one of these. Construct means you need a ruler and a protractor. Okay. So here we go. For A, it is 22 degrees south of east. So I'm going to first draw, it's hard to do both at once. So turn this around. So I'm going to first do a line of action. So I get the 22 degrees right. That's 180, then that's going to be 160, 158. 158, and I'll do a line of action. So line of action is a dashed line that goes on and on forever, as long as you need it. Okay, now I'm going to use my ruler to measure 5.5 centimeters because a centimeter is a Newton. Okay, so 5.5 centimeters puts me right there. And this is about the same as your paper. Okay, 5.5 centimeters. So draw that, construct that. And there's A, force of A. Okay. Now, force of B, we're drawing this as a free body diagram, so they all emanate from the same point. Force of B is 3.5 newtons, 80 degrees north of east. Oh, and on that line of action, just so it doesn't get too messy, I'm going to erase the part I don't need. Okay, so now I need 80 degrees north of east. So that's 80 plus 80 is 260. Right there. Boom. Okay. Now, draw me a line of action. I'll just make them all blue. Draw me a line of action as far as I need it. Okay, then get the ruler out and say this is 3.5 centimeters. Tedious, I know, but still, unless you just love doing sines and cosines. Okay. And I'm just making a point on this problem. I'm kind of doing it the long way. Okay, so there's force B. And then vector C is 60 degrees south of east. 60 degrees south of east. Okay, so the line of action looks like this. Line of action, there's a student asked, what is this line of action you keep talking about? It's just a convenience. It's there, it's kind of a guide to help you. Okay, so this is going to go along this path, this C, somewhere on this path. Okay, and that thing is 4 centimeters long. Okay, 4 centimeters. All right, so these are my three forces acting on whatever the object is. 4 centimeters. That goes from 11 to 15. 4 centimeters. There's force. That is F sub C. Okay, wonderful. Now, the problem is I've now got to add those 3 arrows up. Okay, those lines of action. So I got to take those 3 arrows and put them together. Now, if I have 2 choices. Either I now turn each one of those into a right triangle, get out my calculator, do sine and cosine, do stack and rack, i's and j's, then do that inverse tangent thing to 10-step method, or I do this using head to tail. And head to tail will get me within the pretty close to, you could make a case where you can go up to 2 siggies on head to tail. So what I'm going to do, I'm going to cheat because I have an iPad, but you now on paper and pencil, you take these and you're going to, I'm going to keep the problem on the page, I'm going to start with B. I'm going to start with this one. I'll leave it in place. I'm going to slide C. I'm going to draw a ghost of C. I'm going to slide C up here, and then I'm going to slide A right there, and then I'll get then I could do my resultant, which is very beginning to very end. But I'm going to cheat a little bit, and I'm going to cut out. There's a little scissors here. I'm going to cut out a knife, and I'm going to cut out A and duplicate it. Cheater. So I move that up here. Now now the thing is, that's a ghost. So I made the decision a couple of years ago to make my ghost green. So I'm making all my ghosts green this semester. You should choose a color. You should always, when you're doing physics, you should just have a box of colored pencils with you. So this is force of C, a ghost of it anyway. It's not really force C, it's just a ghost. And then I'm going to do A. I'll cut it out. You got to redraw it. You know, on a test, you can't use your iPad on a test, really. I think within 5 years, all students will have, probably within 4 years, all students will have iPads. So we'll be teaching through iPad. And this is, I mean, I probably won't. I won't be around, but maybe online. So this is, okay. In fact, the physics I teach online, I think I'm going to require iPads. That sounds pretty elitist. No, I won't do that. I won't do that. force of A. Okay, so there's the two ghosts. I've redrawn it. Now the resultant goes from the very beginning to the very end. So I just got to set my ruler on there. And I make it red. I make them, come on. I put the half arrow on the wrong side. I can't help it. It's already a done deal. All right. Didn't anticipate that. Okay, anyway, my resultant goes to the very beginning, very end. Oh, red. So my resultant is here. And that's going to be the length and the orientation. If these three blue forces are acting, that's my summation of forces. If these three blue forces are acting on this object, the object will move, and not just move, it'll accelerate in that direction with that much force. So the next thing is to properly describe this resultant vector. So I take my ruler using the scale and I measure the length, and I'm getting 8 centimeters. That's 8 newtons. 8 newtons at, and now I take my protractor. Oh, I don't have a protractor, but I'll just use this guy. Take this protractor here, 0. That is about 15. So 15 degrees south of east. All right, there is my done. That's what's supposed to happen. Now, let me check this versus the key, the official key. The official key here says 8 newtons, 15 degrees south of east. So I like this better than my official key. I'm going to make this my official key from now on. All right. Oh, and these are ghosts. Green. And now we'll do a lot of ghosting when we do conservation of momentum. And some, really we do it a lot with 2-dimensional collisions. Things hit and then bounce off. We play this game called glance ball, and these discs hit each other and bounce off, kind of like air hockey, but on the floor. And there's a lot of ghosts that you have to draw to do it 2-dimensionally. Okay, you guys are being very quiet. Who has a question? We're moving on now.
I have a question.
Yeah.
How do you decide which vector to start with, to draw the ghost from?
Great question. Matters not. What I try and do is I pick a order so that it doesn't go off the page. I don't care if it goes in the other problems. That's fine. You just don't want it to go off the page. Like one of the practice problems. No, it was problem 5 on 4.6 that a student said, "Hey, Mr. Askey, I had to add paper." So he had folded out a piece of paper, and then because he went off his page. And I thought, well, that's innovative. That took work. He had to tape it on there. But you don't have to do that. So you can add up vectors in any order. It doesn't matter. It's that in that way, vectors add up kind of like arithmetic. 5 plus 3 is 8. 3 plus 5 is 8. So it doesn't matter how you add up vectors. Now, multiplying, it does matter. Multiplying vectors is a royal pain in the butt. There's 2 ways to multiply them. One's called dot product. And turns out when you do a dot product of 2 vectors, you know what comes out of that? Energy. That's where all energy comes from. When you dot forces together, out comes energy. No. When you dot a force vector with a change in position vector, out comes energy. Pretty awesome. When I cross 2 vectors together, no. A force vector and a radius, out comes torque. So those are called dot products and cross products. And we'll get to them. And maybe but we'll get to them. That's E&M is all dot products and cross products. You look at Maxwell's equations, 2 involve dot products, 2 involve cross products. So Yeah, we're getting there. But as far as addition and subtraction, it follows the rules of algebra. Okay.
I have a question.
Yeah.
How did you find the resultant Newton, the 8 Newton?
All I did was I took my ruler. Once I was done, I took my ruler and I measured, I got 8 centimeters. And then I used the scale that 1 centimeter equals 1 Newton. And then I got 8 Newtons.
Okay, thanks.
Yeah. Anything else? We're moving on. If we're good. Okay, good questions. Let's keep going. I'm running low on projectors in my rooms. Kids keep walking off of them, I guess, because I had 40 of them and now I'm down to about 20. Okay, we did that. Okay, now we're going to spend the rest of the time here looking at the front of 4.8. Now, 4.8 is not on the test tomorrow. Although, I mean, there's not that much really new about it. There's a little bit of new stuff, but some of it's just practice. So let's look at, I sent them to the board on number 1. Am I on the right one? Yeah, I sent them to the board on number 1. And so let me turn it off and give you a chance to work number 1 on your own. So I'm going to keep sharing, but I'm going to stop. I'm going to pause. Okay, so let's see where you're at now. This is what they did on the board. You have a submarine, so here's the surface of the water. It's diving 30 degrees with the horizontal. So this comes down, this is a sketch. You don't have to use a protractor. It's coming down at 30 degrees. Follows a straight line path. That's what we have here. So about 50 meters. So they're calling this R. Sometimes you call the combined X, like if it's X, Y, Z, usually you call it delta S, but there's a reason why you choose, see on B it says R. There's a reason why you choose the letter R, because when we're talking torque, torque tends to make things rotate. And so the R becomes a radius. And so that's why a lot of times, I don't know why I chose R there. That was stupid. I should have just called it delta S, but anyway, that's the history of that. So 50 meters, it says, and that's 30 degrees. So, this is basic trig. And so you're trying to find, well, how deep did it go? What's my depth? What's my delta Y? How far is submarine below the surface? And so basic trig, it's the opposite side, so it's sine. So we have delta Y equals 50 sine 30, and we all know sine 30 is 1/2, and that is meters. And so we end up with negative 25 meters. You got to put negative on there because it is going, if you assume down, it's negative. But actually, tell you the truth, the way the question's worded, it says how far, and far is distance. So technically the correct answer is 25 meters. By the way the question's worded, because it says how far below. Okay. B says describe the final position. So that's when we have to, now we have to find out what the X is. And I think when you do cosine, what do you get? 43 right there, 43 meters. If you do 50 cosine 30. And I had a couple of students that kept getting weird answers. You know why? Their calculator was in radians. Unbeknownst to them, their calculator was in radians. Now, if you're in calculus, they work in radians some. So if you're in like AB Calc or BC Calc, you'll come to physics and your calculus in radians, you'll forget. You'll take a test. And then 3 days later, you'll wake up and go, oh my gosh, I was in radians the whole time. All my answers are wrong. So I put a note at the top of the test tomorrow, make sure your calculator's in degrees. Okay. And then a few years ago, I taught AP Physics, and so they would, little pesky little AP Physics students, they would turn they'd put those calculators in radians before the physics kids came in just to mess with them. I thought that was kind of cruel. They got a kick out of it. So component method, then we'd say that R is equal to 43 I roof minus 25 J roof meters. Okay, that's how you would say it in computer talk. Now, if you had time to look at number 2, we did 2 together. So a plane takes off at an angle of 15 degrees horizontal with an average velocity of 10 meters a second, flies its average speed for 20 seconds. So this is a lot like an ACT question. ACT just has physics light. So here we have a plane takes off 15 degrees, and then it goes for, we got V is 10 meters a second. It does that for 20 seconds. And you're supposed to come up with the height, H. I don't want to say delta Y because altitude means height, and altitude can't be negative. Delta Y can be negative. H cannot be negative. So I'm going to call it H right there. This is 15 degrees. What's the altitude? So pretty simple. Once again, well, a little bit, you got to do a little physics, a little red equation physics. My delta S, of course, is velocity times time, so 200 meters. And so we have H then equals to 200 meters times sine of 15 degrees. And that gives us, what do you got? Somebody pipe in and tell me.
51.8.
51.8. We're going to go 2 siggies. We'll say 52 meters. So this obviously is not a jet because it's not going to go faster than 10 meters a second. It's like a drone or something. A drone is taking off. It says a plane, but it's got to be a drone. And then it's about, it's 150 feet up there in about 20 seconds. Okay, those are both kind of boring, straightforward. Let's go to the crux. What the whole point to why you came here today is number 3, most important problem of the day. Because number 3 introduces a new category of physics, and that is called statics. Statics. You will take a course in college. If you go in engineering or you go in any kind of physical science, you'll have to take a course called statics. And static, as you know, means no motion, means not moving at a constant rate, no motion whatsoever, stopped. That's statics. So you'll spend 4 months, a semester of your life, studying things that don't move. And so all the forces acting on those things will have to balance to be 0, right? Newton's first law, the object will not be moving because it can't move, it's static. And so there's all this concepts that go with things that don't move. Like if you're going to be an architectural engineer, you're trying to design a house that doesn't move. You want the roof so that it doesn't collapse. And so you're going to do what's called truss problems. You'll have cantilever bridges and things like that don't move. And so that's called statics. And so when we're doing statics with forces, we want those forces to add up to 0. Okay, so that's the idea here, is we're introducing statics. And we'll start this problem. We're not going to finish it today. We'll finish it on Friday. One man is pulling on rope A with a force of 650 newtons. So that's going to be the big one. And I apologize. This summer, I have got to redo this. I'm going to make a note after we're done here. I got to redo this. That thing shouldn't be, that was a little to space out, say, hey, here's your drawing, here's your work. But now in the last 10 years, I wrote this thing like 10 years ago. In the last 10 years, I do a lot of the work on the drawing. So your drawing, so I apologize, ignore that, but your drawing should be as big as you need it. So this doesn't require a ruler or a protractor. We're sketching it. We're going to use sines and cosines to solve this. So I'll draw the biggest one is this 650 newtons. Oops. That's my biggest force, 650 newtons. So I'm going to draw it first, and then everything else is relative to it. So I'm just going to make it long. 650. I'm going to make this long. I'll go ahead, because this is a kind of a key. I'll go ahead and try and make this one nice. But you can be a sketch. All right, so this is the force of rope A, and the force of rope A is equal to 650 newtons. So that's my length, my relative length. The other end of the rope is tied to 3 other ropes. So there's a knot. There's a knot right here. And there's 3 other ropes coming off that knot. Now, ultimately, we don't want the whole system. This is called a system. When you add up all the force, look at them all together, that's called a system. And the whole system can't move. See, back here, going back to this for a second, this car, this is, the whole thing is, okay, here's another preview of things to come. This whole thing is called a system. And so once you've established your system, you do a, like, okay, now we're getting into thermodynamics, but I'm trying to give you concepts that'll get you through lots of classes in college and things that bothered me when I was in college. Remember, I didn't have high school physics, so this is a virtual special here. See, I'm doing this dotted line around the whole thing. I've claimed my system. So this is, and depending on how you make your system, like when you're doing machines, you'll have pulley systems. You'll have pulley systems attached to levers, then you'll have those attached to gears. And you got to say, well, I'm calling all of it one system, or I'm calling this little part of system A, this part system B. Same thing with astronomy. We can call the Earth Moon one system and treat us as one. And we all kind of go around this, what's called a barycenter. We orbit a barycenter. Or we could say the Earth Sun is one system. Or we could say the sun's its own system and the Earth's its own system. See what I'm saying? So this is a Newton idea. And Newton said, you can keep making your system bigger and bigger and bigger until it includes the entire universe. And that's the ultimate system, right? Or you can make your system a quark if you're looking inside. So when you're doing a physics problem, you have to say, okay, what's my system? All right. I got to remember to say that in class. Friday. So our system can't move, and our system will be all 4 forces together. So there's 650 newtons going that way. The other ends are tied to ropes. One man is pulling on each of the other 3 ropes. Rope B is oriented 60 degrees north of west. So I'm not going to get a protractor out, but I can kind of guesstimate 60 degrees. I'm going to draw a line of action. Line of action. I'll keep blue. And the line of action, remember, it goes as far as you want. It's a guide. So there's B, and then it says rope C is 20 degrees north of west. So rope C is going to come off this way. Okay, now I'm going to actually draw the vectors. So rope B is, it says rope B is, how big is it? It is, I don't like where I worded this. I know it's hard to read. Okay, rope B is pulling 120 newtons. So if this is 650, I happen to make it 6. Oh, I didn't. I keep changing my scale. Okay, I'll get it close. Hold on. Okay, then B is 120 newtons. So it's not very big at all. B is just this long. No. Sometimes iPads are a pain in the butt. Nothing more convenient than a good old pencil and paper. Good grief. Look how small that is. There's B. That's going to stink. I'm going to erase this now. I don't need that line of action anymore. We're getting close to being done, I promise. We're not going to finish this. We're going to get started. There's little tiny force B. Force C is 200 newtons, a little better. Okay, hold on. 200 newtons, this is C. Looks like that. There's force C. Force C, and let me erase its line of action. Okay. So I have these three forces. Well, obviously, force A is the dominant force. And if I left these three alone, this is not going to stay still. So I got to bring in a man D, a person D, to throw a rope on it and stop the whole thing from moving. Okay. So we can guesstimate right now where rope D should be. We can see that obviously it's got to be in what quadrant would you say? To get the whole thing to stop, what quadrant does rope D have to be in?
Would it be the third?
I would say somewhere in the third. Now, I don't know what the angle is, but I'm going to guesstimate that rope D, yeah, I don't know, maybe it's kind of a guess. It's good to have a guess. We'll get it exactly, but my guess is that it's going to look something like, would that stop it? Maybe a little longer. Just you kind of ballpark it. Okay, that seems like a force of D, question mark, but that's my guess. You got a first guess, then you'll get it exactly right. Okay, now I could do this head to tail. There's a way to do it, but I'm going to do it with the I's and J's and stack and rack. But first, before we do, we're going to do that on Friday. But first, let me give you a new word. What I'm looking for, force D is going to stop any potential motion, right? And so vectors, here we go. Write this down. Here's your new word. Vectors, a vector, a force vector, let's get specific. A force vector that stops or cancels, I'll say cancels, that cancels any potential motion is called an equilibrant. Brunt, not equivalent, not equivalent, equilibrant. So say it with me. Equilibrant. Now say it again. Equilibrant. Now say it 3 times in a row. Equilibrant, equilibrant, equilibrant. Okay. Not equilibriant, equilibrant. And so what we have to do is, that's what be our task on Friday. This is not on the test tomorrow, obviously. But our task on Friday is to figure out how to figure out that equilibrant. That's what force D will be. It's like if in the Super Bowl, Tom Brady's doing a quarterback sneak and the whole line's moving into the end zone and some linebacker comes up and stops him in his tracks. He adds a force to the system that stops the system. That linebacker is the equilibrant. Okay, he stopped it from its motion or from potential motion. Okay, so last thing, equilibrants, and maybe write this nigger note here. Let me get short work over there, but equilibrants, and then you can go. We're almost time. Equilibrants turn dynamic systems or potential dynamic systems into static systems. Now, if you are an architectural engineer, you want to do that. Or you're building a bridge. You would like to bring a cantilever in or bring a truss so that stops that bridge from falling down. That is the equilibrant you need. And so we'll study the physics of equilibrants starting on Friday. Okay. Yeah, I'll stop sharing. All right. Questions? We will not be
So
tomorrow. Go ahead, say Rose.
if we have an iPad, we can't take the test on it.
Here's the problem with that. I can't grade it. I want to be able to annotate, and circle, and write notes. I can't do that on an iPad. See what I'm saying? So
Can you not do the same thing you do with like
oh,
your app on the iPad, and you can annotate the PDF someone sends to you?
yeah, but I got to do all that work. I mean, I have a stack of papers to grade. I don't want to have a stack of PDFs and then to transfer over to my program, and then that's just even more hassle. If everyone's using an iPad, okay, but I want everyone to have. What you can do is you can do it on your iPad and then print it off. Okay, I'll go halfway with you. Print it off then, and then, but I still want your paper copy. So because I want a stack of papers. Call me old fashioned, but I've got to be able to, because then I'll compare your paper to other papers. See what I'm saying? I mean, I have a stack of papers. I graded one problem at a time. So I don't want to get out 70 papers and then all of a sudden 5 are an iPad. You know what I'm saying? So I'm not ready for that yet.
So I'm flying out of here at 10:15 on Friday morning. So should I just take the test like that evening whenever I'm in?
You have till Saturday too. You can take Saturday if you want.
Okay.
Saturday by 6. If you will, you'll have to email it to me. If you can't get it to my porch by 6 p.m. Saturday afternoon, then you got to email me by 6 p.m. Saturday.
Yeah, I'll email you because I won't be back until Monday.
Yeah, and then I'll print it off. Without, I mean, as long as there's not too many people, it's not that big a deal. But I don't want to print off, 15 PDFs if I can help it. Okay, great guys. Thank you. See you guys Friday. Yeah. Bye-bye.